Hello everyone. Sorry this took so long. I was trying to make this lecture as enlightening as possible. I was working on some code in order to, well, not really code, but I was working on some scripts to make the visuals a little bit more, uh, I guess it's just to provide a better visual aid. So that took a little bit longer to make, and I apologize. But this lecture today is going to be about representation theory. And originally, I was going to jump through this one and talk about Lie algebras and Lie groups, but then I realized that it's very difficult to talk about the relationship between the two without representations. I decided to do an intermediate video on this, on basically representation theory. So let's go. So the outline of this lecture is as follows. First, I'm going to summarize what we did in the last lecture. Then I'm going to define what a representation is. Then I'm going to talk about what equivalent representations are. Finally, I'm going to show you what invariant subspaces are and how they relate to irreducible representations. And in all of these sections, I will discuss a little bit about the physical applications. So let us summarize what we did last time. In the last lecture, we defined a vector space V and its dual space of this should be V star. So apologies, there's a minor mistake. So there should be a V star here over some field F. So a vector space is defined as follows, and its corresponding dual is defined as follows. And after this, we define the Hermitian inner product. So the Hermitian inner product is basically a mapping such that if we have a vector space and a vector space, or a vector space and its dual, it maps to a complex number, and it must have the following properties, namely there has to exist conjugate symmetry, linearity, antilinearity, and positive definiteness. And after that, we kind of talked about the issue with infinite vector spaces, as summing infinite elements may yield to an element that is not in the vector space. So then we have to define something called Cauchy completeness. Basically, all vectors in the vector space must converge to a limiting vector. And for a Hilbert space to exist, basically, it must be Cauchy complete. And this is basically the arena of quantum mechanics where we do computations and etc. So in addition to this, we talked about how this relates to group theory, and we showed that the hydrogen atom basically has many, many different energy levels. So basically, it is part of the zentrum of the general linear group, because this includes all operators that commute. And we showed that the operators that corresponds to the hydrogen atom commutes. This leads to two cases: one, coherent states or degenerate states. And we can clearly see that the hydrogen atom is degenerate because they have the same eigenvalues, but different eigenstates, which means they have different eigenvectors. So the hydrogen atom is an example of a degenerate state. We also showed what happens when you break the symmetries of the group. Then you lead to something called the Zeeman effect. Basically, you alter the Hamiltonian in such a way that it no longer commutes, and basically the degeneracy splits into these lines, which I talked about last time, and I thought it was quite beautiful, so I decided to add this into the lecture. And with that, now we can talk about what we're going to do in this lecture. In this lecture, we're going to talk about representations of a particular group. So for some group G and a vector space V over some field F, a representation of a group G is a homomorphism between the group to a general linear vector space, such that the operator that acts on the identity in the group yields the identity matrix in the vector space. And yeah, so basically the beauty of group theory is that it is quite generalized, as it is the language of symmetry in mathematical terms. However, in an attempt to make the language more general, it becomes quite abstract. Therefore, in order to make sense of these abstractions, we need to choose a representation for a particular group. In the next lecture, I will talk about how these are related to quantum mechanics. And here, let me just talk about representations from previous groups that we've already defined. So in the first lecture on group theory, I showed that the set of translation operators is a group. So basically like this. Well, I have been slightly deceitful in that I did not tell you that the expression, this following expression, is a representation of this group. So let us assume that we don't know what the representation is, but we know how this translation operator acts, namely the dot product between the translation operators yields the sum of the vectors in its argument, where TA2 equals TA minus 1 is the inverse, and T0 is the identity. So can we define a representation for these operations? So let us consider the transformation of position-dependent functions in one dimension, so namely f of x. Recall that if we act a translation operator on f of x, we get f of x plus x naught. So recall that the Taylor expansion about A is as follows. So we get the following expression. In the above equation, we cannot see that the function we cannot see basically this function f of x plus x naught, but we can perform a transformation such that x is equal to x plus x naught, and therefore A must be, and A equals to x naught, and therefore we get the following expression. So we can see that the sum to infinity from n equals 0 of alpha x to the n over n factorial is the exponential function of alpha x. So since f of x is purely a function of x, we can write partial x as d dx and can be written as follows. And what we see is this is, in fact, the translation operator. So this factor here can be defined as the translation operator, which is exactly the same as what we've written here. But in the previous example, it seems that we are cheating because we already know that the Taylor expansion is the mapping of the group onto the vector space, as this is how we define the translation operator in the first place. Thus, this argument seems, it's not exactly circular, but it seems somewhat circular. But let me talk about another example where we did not define a representation. So last time I talked about the quaternions and how they can be considered as vectors under the geometric product. In this case, let me show you another representation of this group as matrices. So recall that the set of quaternions can be written as follows. So let us multiply h by ijk. So then we have k times h is equal to this, j times k times h is equal to this, and I times j times k equals to this, times h equals to this. And if we multiply by -1, we get back on itself. So we can write this as a 4x4 matrix, right? So basically, ABC corresponds to this one, minus D minus C BA corresponds to this one, and then etc. Right? This one corresponds to this one, and this one corresponds to this one. So we can separate these matrices by factoring out A, B, C, and D as follows. By decomposing the matrix in this fashion, we can see that this matrix corresponds to unity. This matrix corresponds to J. This corresponds to I. This matrix corresponds to J, and this matrix corresponds to K. Hence, we have the map, but we have to remember that the map from the quaternions to the matrix, it's the representation, not the matrix itself. The matrix itself are called the matrix itself are called generators, and they are the elements of something of the algebra that corresponds to the group, which I will talk about a little bit later when I talk about the algebras and the groups. But we have to keep in mind that since the structure of groups is quite general, it's not like differential equations where you set the equation and the boundary conditions or initial conditions and you get a unique solution. Representations are not unique. So, for example, we could have multiplied by ki squared to yield this representation. And hence, we have different representations for the unity I, j, and k. See, these are quite different. And we can see that for a particular group, we can have many different representations, as we can have many different transformations to yield a vector space. So now that I've talked about representations, let me talk about equivalent representations. So let a group map to two different vector spaces, V and W. When I say different, this is kind of, I guess they don't have to be different. They can be the same vector space, but for generality, we can just say they're different. So via the representation, the following. So basically, given a map, right, phi1 and phi2, from the group to the vector space and from the group to another vector space, the representation is equivalent if there exists an invertible operator from the vector space V to W such that the following is true. To illustrate this point, let us show that the two illustrated representations in the previous example are equivalent representations by finding a map K. But let us recall some results from linear algebra, right? Let the representation phi sub 1 of H equals H1 and phi sub 2 of H is equals H2. Basically, there are two different representations of the quaternions. However, suppose that the matrix H1 and H2 are diagonalizable. Then the diagonal matrices are as follows. So D1 is equal to some matrix times its inverse and then H1. And the same with D2, right? Now, recall that if the representations are equivalent, we can multiply K on and K inverse and sandwich them between H1 to yield H2 to yield H1. But if we substitute this expression in terms of D1, so basically if we multiply lambda sub 2 on this side, we get, lambda inverse on this side, we get lambda inverse here, and lambda sub 2 here, to get H2 equals lambda inverse times D2 times lambda sub 2. And we get this. We get this expression where T is equal to K times lambda sub 2 inverse, and T inverse is just basically the inverse of both of these, and then you swap the order of multiplication. So since these two expressions are equivalent, if the matrices are similar, D1 equals D2, there exists a K equals to lambda 1 times lambda 2, such that the matrices are similar, which means that the similar matrices imply the equivalent representations. And with this, let us look at an example in Mathematica. So let me share another screen. Let me see how I can do that here. So let us share. Give me a second. Why is that not? Give me 1 second. Stop video. Stop sharing. Let's see what's going on. There we go. So now that I've shared my screen, we can see this. And basically, I've written a Mathematica script to show the equivalent representations. So let us see. So basically, I've written the two different representations here. Right here, right? So we have two different representations, H1 and H2. So we want to show that they're equivalent. So what we're going to do is, first we're going to check whether the matrices are diagonalizable. So let us do that. So, I have not run the matrices here. So let's run it first. And then now so basically, if it's false, then we cannot do this. We cannot use this argument, but I did not run the matrix beforehand, so it should yield true. So if we do this, we find that the matrices H1 and H2 are diagonalizable. But what happens is we also need to check that their eigenvalues are equivalent. So by doing eigenvalues H1 and eigenvalues H2, we get these two expressions. And in principle, this is enough to show that the matrices are similar, but just for completeness, let us display the diagonal matrices. So I'm going to clear the definitions here. Then I'm going to, basically what I'm going to do here, I'm going to transpose the eigenvectors and construct them into a matrix of, so basically diagonal matrices. And basically what this does, it just constructs the diagonal matrix. So I'm just going to do these for both of these matrices. And we can see that the diagonal matrices for H1 and H2 are exactly the same. So they are similar matrices, and this implies that they are equivalent representations. So now let us go back to the lecture slides here. So now that we've defined equivalent representations, let us talk about invariant subspaces and irreducible representations. So an invariant subspace is basically if we have some map F from some vector space to this should be W, sorry, one of these should be W, sorry, this is my mistake, one of these, then W is an invariant subspace if F of some vector is in W, and for all vectors in W, it's also in W. So with this, we can define an irreducible representation. So a representation is irreducible if the representation phi of G to some general linear group, some general linear vectors, so a general linear group which yields a vector, a matrix basically of a group. Basically, the representation is irreducible if and only if the invariant subspace is V itself. So the irreducible representations are important because they allow us to determine the generators. And I'll discuss this in the next lecture when I talk about the algebra and the groups. And the generators determine significant physical quantities in many cases. So let us look at an example of an irreducible representation, namely of the group SU2. So this is crucial in quantum mechanics, as you will see when I go through the steps. So recall that SU2 is the set of unitary matrices such that they're basically set of unitary matrices and with determinant 1. So basically, if we label these A, B, C, D, we get U, and U dagger must be this. Basically, we take the complex conjugate of each one and transpose the matrix. And for this, the SU2 group has the solutions as follows. But despite the restrictions on the group, this equation has infinitely many solutions. This is why SU2 is an infinite group. But one particular solution is if we set A equals to D bar and B equals to minus C bar. And for simplicity, let we get the following. It should be a minus, I think, but it doesn't really. Actually, no, this is fine. This is fine. For simplicity, let A and D be I times the real number. So basically, it's not a complex number, but it's just an imaginary one. Where it is a complex number, but you just set the real part to 0. So we find that, and moreover, let B equals to minus Y plus IX and C equals to Y plus IX. So there we get we have a matrix which is in the set basically the set of unitary matrices as follows. And we can decompose this into invariant subspaces, and we get Ix times this, Iy times this, and minus Iy times this, and Iz times this. And this may look familiar to you. These are the Pauli matrices that describe spin in quantum mechanics. So this is the x, sigma sub x, sigma sub y, and sigma sub z. So this will so basically the Pauli matrices are a faithful are irreducible representations of the SU2 group. So this is quite an interesting thing. So this is quantum mechanics basically is a natural representation of a something quite fundamental, something quite general. So I remember talking about the Bloch sphere in my classical and quantum optics lecture, and you can, because these are irreducible representations, you can define them as basically the set of basis vectors, and then by transforming them, by rotating them, you can get another vector that is basically this a hat is the sum of the representations sigma sub 1, sigma sub 2, and sigma sub 3. So this is quite a beautiful representation of a geometric representation of SU2, and I got this from a paper in the journal Physics B and by Fang et al. So now let us look at an example of groups and representations in chemistry, namely molecular modes and molecular vibrational modes. So the normal way that you would solve this problem is to write a Lagrangian, something like this, and then you solve the Euler-Lagrange equations. For particles, for molecules with not that many atoms, it is relatively easy to solve, as there are not that many degrees of freedom. But for basically molecules with many atoms, this can be quite complicated because you would have to compute many different normal modes and etc. So you would typically opt to solve this computationally, but there is another way to solve it using group theory and irreducible representations. So let us to identify basically the normal modes, we have to first determine what symmetries there are. So this illustration I got from Wikipedia basically shows that how we can make something invariant. So basically, a symmetry is basically a set of transformations that leaves the original state invariant. So basically, you can see that if these A, B, C, and D are indistinguishable. Basically, they're the same label. We can rotate it by some factor of pi over 4. Pi over, what is this? 2 pi over 4, pi over 2. And then we can reflect it about this axis to yield something that is invariant. This is one of the symmetries of the group, and this is called the S4 transformation. And basically, it's defined by a rotation by this, and then a reflection by about this axis. So, as mentioned before, there are two kinds of fundamental transformations, namely rotations and reflections. Excuse me. Hence, the set of transformations forms a subgroup of O3. And the reason why it is not a group of SO3 is because if we include reflections, we can invert one of the axes, and hence the determinant can be -1. And to identify the symmetries, we have to find the transformations that leave the molecule invariant. So let Cn denote the rotations by theta equals 2 pi over n. Sigma d denote the rotations about a plane that contains a central atom. And in the previous figure, we can also show that the combination of rotations and reflections can also yield a symmetry, namely S4. And with the benefit of hindsight, we know that the group symmetry is this. But I will show you this more visually in Mathematica as well. So let us see. Hopefully, when I share screen this time, they will. Okay, I have to do something again. Maybe if I open this, share, and then if I open it here, it will show up. CH4 axes. Okay, so basically, one of the symmetries, right, is basically if I line the atom like so. So let's do this first. This is a tetrahedral atom. So if I align the atom like this, we can rotate this atom by 2 pi over 3, namely 120 degrees to yield the same thing. We can also reflect it if we align the atom like this. It's a bit hard to drag. So if we have it like this, right, we can also reflect it about this axis, or this axis. And also, if we align the atom like this, sorry, this is taking a bit long. Something like this. Maybe it's hard to drag, sorry. Something like this. We can, sorry. Something like this. We can rotate it about pi over pi 2 pi. So by pi to yield the same configuration. So let's look back at the other slide. So now from this, we can also deduce the reducible representations. So although TD is not strictly a subgroup of SO3, we can separate the transformations into two different ones, namely ones of rotation and the others of reflection. So the SO3 transformation is as follows, and the reflection is like this. If we're reflecting about the XY plane, we can, as shown before, we can reflect about different planes. So this is these two are the reducible representations. And what you can do is notice that these are in block diagonal form. So you can just cut this here. This is a diagonal. So this is block diagonal, right? So this is not diagonal. This is not diagonal. But if we cut it like this, you have two. This is in a block diagonal form. So what we can do is we can write it in the following manner, similar to that of the Quaternions. So basically back here, or here, right? We can here. We can write it like this. So these are the irreducible representations. We can also write it in this manner to obtain the following. And for the reflection one, we can write it like this. And for those who are chemists, we can convert this to Mulliken notation to write a character table. This is done by taking the trace of the irreducible representations. So if we have so basically, if we're only considering this matrix, right? So A1 corresponds to only considering this one. So if we consider this one, we get basically all the traces will be 1. So trace, if we perform this transformation, we get 1. If we act on the identity, we still get 1 here. So the trace is still 1. If we act on C2, we still get 1 here, so etc. A2, on the other hand, we have to replace this with -1. Is that correct? We have to replace this. No. Sorry. When we perform reflections, basically, we replace this. So basically, sorry, this A1 is only considering reflections about XZ. So basically, when we take the trace, so let me restate this. So basically, E, the corner one here is 1, so the trace is also 1. For these two, it is similar. We also have a trace of 1. Here, you would question why the trace is not -1, because here we have the -1 here. But this one is considering reflections about XZ. So the Z is left unchanged. But this will change if we have A2. So A2, the same thing is with these three, since we're only doing it in the XY axis. This trace element is invariant. But these two are different because we're now considering reflections about the XY one. So this changes to -1. And the reason why this one is also -1, because these two, the technical name for it is they're in the same conjugacy class. So these two are -1. But this is not always a strict rule, right? For these two, we have two different ones. And the reason is because the way that okay, so E here is the trace of the above two elements. So if we take these two, right? So if this was the identity, so C sub n is the identity, sorry, not C sub n, sorry. If E is the identity, so we have 1, 1, 1, so 1, 1, 1, right? So if we take the trace of the first matrix, the first diagonal matrix, we get 2. For C3, we have to put 2 pi over 3. This is -1/2. So -1/2 plus -1/2 is equal to -1. For this one, you get similar. You get basically plug in pi over 2. So sorry, plug in 2 pi, not 2 pi. Sorry, plug in pi, and then we get 2 here, and then here you get 0 and 0, because when you take the trace of this one, basically reflections, you essentially get 0 here because you get 1 and the sum. So basically, if we're if we're reflecting about XZ, you get 1 and -1. So the sum is always 0. And this is this for the T1 and T2. This is considering the trace of the trace of a 3x3 matrix. So these two they yield these two character tables. You can also determine the character tables of the point groups using the great orthogonality theorem, but I find it easier just to take the trace of the irreducible representations, and I will note that this is just my opinion. So now that we have the character tables, what we have to do is use the following equation to deduce the representations for the molecular vibration, where gamma sub EQ is the equivalent representations of the atom site, and gamma sub vec, gamma sub t, and gamma sub r are the representations of the vector, translation, and rotation. Sorry, this should just be rotation, not rotational. So rotations about the center of mass. And gamma sub v is essentially the sum of all fundamental modes of vibration. So in the tetrahedral case, we have the inner product. This is the tensor product of 2a1 plus 2 t2 tensor product t2 minus t2 plus t1. This should be a minus. Sorry, this should be a minus here. My mistake. Minus. So then we get a1 plus e plus 2e t2, which yields 4 fundamental modes of vibrations. But recall that there are also overtones, as the linear combination of two normal modes is also a solution to the equation of motion. So they can be summarized in this table below. So we have A1E, T1, T2 are the fundamental modes, and they have the corresponding frequencies. Remember that these frequencies can be different for different molecules. These are obtained from experiments. So, but we can also have overtones by combining the fundamental modes. So we have A1 plus A2 plus A3. A1 plus A2 plus E is an overtone. A1 plus E plus T1 plus T2 is also an overtone. These are all overtones, right? They're basically just subbing the normal modes. So this is the power of group theory by using the representations, the irreducible representations of the vibrational modes. We can determine the fundamental frequencies or fundamental normal modes, and then sum them together to obtain the overtones. And to determine whether they are infrared active or Raman active, you can use selection rules in quantum mechanics, which I will talk about later when I talk about parity operators. So maybe to end this lecture, I should end on something more nice, something more beautiful. Namely, we have these are the normal modes of CH4. So this is how they transform. So some of them are basically the molecules are drawn towards this. Sometimes they are drawn away from it, and etc. So this is quite a nice representation of the normal modes of CH4. So in the next lecture, I will talk about Lie algebras and Lie groups. And that's actually my favorite topic to talk about, because not only does Lie algebra and Lie groups have a close connection to quantum mechanics, but it also has a close connection to general relativity. So I hope you look forward to that, and see you in the next lecture. Thank you.